So we have three different types of equations of quadratic functions, or the way that we can write them. And then depending on the form that we're given, we can pull out some important information. So remember that anything that has the highest exponent of 2 is going to be in the quadratic function family. We can identify that something is a quadratic because it graphs the parabola. It graphs a U-shaped graph. So for a parabola, we can actually write that in three different ways. The first is the standard form, ax squared plus bx plus c. The only thing that we can pull out relatively easily is that this is c value is going to be your y-intercept. The one in the middle is the vertex form. And so to use vertex form, the h and the k represent the location of the vertex in the coordinate plane. And then the last one that we're going to look at is the factored form. And so when we factor a quadratic, we can easily see the x-intercepts. So we'll look at each of those and how to work with those and manipulate a little bit. So all three of those forms start with an a term. So that, remember when we talk about transformations, the a term is the stretch or compression. It makes the parabola wider or narrower. Also, if that a value is a positive, the graph is going to open up. But if it's a negative number, the graph has been flipped over and it's going to open down. So on this graph over here, I can look at this graph and know that even without finding it, the a value has to be less than 0 because it's been flipped across the x-axis. All quadratic equations have a vertex. So that is, again, the turning point of the graph. It's either going to be a maximum or a minimum. In this case, this one would be a maximum because it's a high point on the graph. And then remember that we talked about the axis of symmetry, so the line where we can fold that parabola in half, and the graph would be exactly symmetrical on both sides. So on this one, it's x is equal to 1. That would be right where the midway point of the parabola is, and also your vertex sits on your axis of symmetry. And then on this particular graph, the quadratic function crosses the y-axis at 0, 3. So it's only going to cross the y-axis one time, but we're going to have two x-intercepts. So this one looks like it's maybe a little bit past, but we'll say that one's at -1, 0, and this one is at 3, 0, sorry. Three, 0. So this one is going to cross the x-axis twice. So the vertex for this one is at 1, 4. We already said that the y-intercept is at 0, 3. Axis symmetry is at x equals 1, and then the x-intercepts at -1, 0, and 3, 0 for that particular graph. So if you're given the standard form of an equation, remember that we can find the axis of symmetry by taking the opposite of b over 2a. The vertex is going to sit on that point. Your y-intercept is your constant. So remember that we talked about the constant. If I plugged in zeros for all the x's, we would be left with just the y-intercept. So just some of the shortcuts and things that you can use for that standard form of the equation. The one that we haven't looked at or spent as much time on at all in this course is the vertex form. So vertex form uses this idea of a perfect square trinomial. So we've been looking at perfect squares the past couple of days. And so when we have the same expression squared, then we would call that the perfect square. If a quadratic function is in this form, it's easy to identify the h and the k because it's part of the form. Now we do have to be careful because the minus sign belongs to the function rule. So if I had a positive in there, it's actually minus and negative. So we do need to be a little careful when we're identifying the vertex. It's always going to be the opposite sign of what we see inside the parentheses for the h value. The k, again, is your vertical transformation, up and down, and we don't have to worry about the opposite of that. But if you remember with left and right translations, it was always the opposite. If it was a negative, it moved it to the right. If it was a positive, it moved it to the left, which is the opposite of what we would expect. And again, the a value in the front just talks about a stretch or compression. And if it's a negative number, then it's going to open the parabola down. So this graph for f of x equals 2 times x minus 2 quantity squared plus 4. Just looking at this, I know that it's going to open up because it's a positive number in the front, which means that graph is going to have a minimum for the vertex. And remember that it's the h and the k, so I just pull those numbers out of the function rule. So this would be a 2 for h and a 4 for k. That's all that we have to do if it's already in that form for you. On this one, it's a negative 4 in the front, which means the parabola has been flipped over. And so then again, we know that we're going to have a maximum. Our h for this one is a positive, which means when we get ready to write it, it's a negative 3 and a negative 5. So again, if you have a positive h value, that means that your graph has been shifted to the left. If you have a negative h value, that means your graph has been shifted to the right. And again, go back to what you know about transformations. All of that is connected. And then this one has been moved down because it's a negative 5. So shifted down 5 units. The first one would have been a 4 because it's been shifted up 4 units. We can also convert from standard form to vertex form to be able to see this without graphing. Now this is probably not the easiest way, but I just want you to know it is something that we can do. And you'll do a lot of it once you get into pre-calculus. So being familiar and comfortable with this now is a good idea. So we're going to do the same process that we learned for solving equations. We're going to leave a space. The difference here is that when we had the equations, we wanted to balance, but now we're working on the same side of the equation, which means I want the net change to the equation to be 0. So whatever I add to this, I also have to take away, because if I add and subtract the same amount, I've really changed this by nothing. And then we're also going to push so that 71 gets pushed to the outside of the parentheses. So you say I have the same 3 numbers I started with, but I've given myself room to complete the square because I'm going to make this a perfect square. So half of 16 is 8, and 8 squared is 64. I'm going to add the 64, but I also have to subtract it here. And then we're going to simplify. So this would be x plus 8 quantity squared, and then 64, or negative 64 plus 71 is going to be a positive 7. So without graphing, I know the vertex of this parabola is going to be at negative 8 because I take the opposite of the 8 and then positive 7. So this is vertex form. This would be the vertex that I can find easily in that equation. The second one has something a little different. I still have a coefficient of 1, but I have a negative sign out in the front. And so when we simplify one like this, we're going to group together the negative x squared and the negative 14x, and I'm going to leave the negative 59 out here. And again, that's because we're completing the square inside parentheses, but I don't want the negative, so I can actually factor that out of both terms and change the sign. Leave a spot to complete the square. I have a 59, and then I have to subtract whatever it is I add inside the parentheses. So half of 14 is 7. 7 squared is 49. Now, we want to be careful because when we have a negative out in the front, we didn't actually add 49, it's a negative 49. So back here, we're going to make that a negative 49. So if I really subtracted it the first time, to keep that in balance, I have to add. And then we simplify. And so that would be that function rule in vertex form. I know that this is going to have a maximum because it has a negative sign in the front. And the vertex would be at -7, -10. Now, admittedly, this is not the easiest way to convert. The easiest way to convert to vertex form is to use technology. So I went ahead and graphed my function rule in Desmos, 2x squared plus 36x plus 170, and I found the vertex. I could have also done that algebraically, right? We could have taken the opposite of b over 2a, which would be -36 over 2 times 2, so that would be -36 over 4, which is -9. So we see that here we have the -9 for the x value for the vertex. That's where the axis of symmetry is. To get the 8, you just plug in the -9. And I'm not going to do the algebra, but if you did simplify that, you would get 8. So all we have to do to convert this is plug in for the variables. Your a value is always the same. So if it's a 2 in the standard, it's going to be 2 in vertex. We would do x minus a -9. That's why it turns that into a positive squared. And then we plug in the 8 for k. So 2 times the quantity x plus 9 squared plus 8. So there's no reason not to use the technology that we have to help us with converting to vertex form. And then the last form is factored form. And so this is just giving us the x-intercepts. So we can take each intercept, set it equal to 0, and solve for x. So I know that that graph of that parabola is going to have intercepts at 6 and 2. The axis of symmetry has to be right in the middle. So between 6 and 2, there's 4 units total. Right? So if I have one at 2 and one at 6, and I would divide that by 2, so it's going to be 2 units away from each, which means that graph would have an axis of symmetry at x is equal to 4. So you can use that form to help you with intercepts, but then also to quickly figure out what the axis of symmetry would be. For the second example, it doesn't matter what is inside parentheses, we just take them and set them equal to 0, solve for x to get the intercepts once we're in factored form. So -1 to 4 is 5 units, so it would be 2.5 units away. So the axis of symmetry on that graph would be at 1.5. So each of these has a different positive to them and different ways that we use them. But being able to identify vertex form is going to be the one that we're going to use most often.